All right. Skip right there. Uh, Hello. I'm gonna record video hopefully after Thanksgiving. I'm not sure. Earlier for today. Um, the today record video for chapter 7 and discrete circuit amplifiers. Um, in the previous session, we're gonna learn about the basic configurations from um, the basic operation of the OP-amp, amplifier operation. But from now, we're gonna just the one of them, discrete circuit amplifiers, the type, and then we're gonna try to understand operation of the discrete circuit amplifiers. What is the discrete circuit amplifiers? Um, this is analog amplifier circuit composed of individual components such as transistor, resistor, and capacitors. It is suitable for learning and design purpose to deeply understand and control the operating principle of the circuits. Okay. Um, so um, So the in this chapter 7, they deal with the two different type transistor amplifier circuits. The one is the BJT, the other one MOSFET, right? The BJT bipolar junction they're gonna using usually for high current gain and suitable for circuit required strong the current driving, while the MOSFET has the high input impedance, okay, making it suitable for circuit requiring voltage amplification and then the integration. As I said before, there are a lot of options for the application transistor amplifiers, but in here, the one of them is most popular, the type for the BJT and MOSFET. The BJT is common emitter amplifiers, which has no any components between BJT and the ground, and also the common sources, the circuit that was amplifier, there's MOSFET. That is also there was nothing, they do not have any components between ground and the MOSFET of the common, just like the source part in the here. So especially in the MOSFET part, we're gonna explain. We will explain to the basic operating principle and circuit the elements. All right, so I think we have already learned before in the lab session, but I wanted to very quickly go over for the again in the common source, the MOSFET and BJT as well as a really basic operation. For this slides, introduced to the common source amplifier, the base on the MOSFET. Figure 7.57, you can see that V subsignal and then R subsignal as well. And then the voltage divider biases, in here, the capacitor, okay, and also the load resistor and the output voltage here. So in the figure A, the first circuit contained both the signal paths as AC operations and biasing paths, especially at the DC bias. In this case, right there, the free sub G. But for the easier analysis, we usually separate them. In the complete circuit A, the capacitor system 1 to S, that was passing AC signal, means the capacitor is working as the short circuit we learned before, but the block, the DC circuit, okay, the capacitor in the DC, that was working the open circuit, okay. This is the infinity. So it means we can, separate it independently to analyze more clearly. So we can remove signal sources and leaving only the DC biasing circuit. So as I said before, the capacitor is the open circuit. So the only remain part is voltage divider bias, circuit here. Okay, so R sub G sub 1, R sub D, R sub G sub 2, R sub S, so on. Okay. Um, so for this case, the common source amplifier, is to be biasing four register R sub G sub 1 and R sub G sub 2, R sub S, R sub D. This is 3 sub D, 3 sub S, and 3 sub G. Okay. All right. So now we're gonna just the introduction to configuration for the MOSFET. But I wanted to more focus on for today the common emitter amplifier, the based on the BJT. Similar, but it's different. Okay. So the common emitter amplifier is most widely used for all of the BJT amplifier configuration. It's very important. So its main purpose to amplify small input signal into larger output signal. Definitely, they have to also phase inversions. Very important. Okay. So means the input V sub in, the output minus V sub out. Okay. So the gain is V sub 0, V sub in is minus value. Okay. So the input is the base terminal. The output is the collector terminal. C, B, E. We learned before collector, base, and emitter. Okay. Especially the common terminal is like the emitter terminal. For this case, the voltage divider is like the connection of ground. Okay, so maybe again, so common emitter amplifier has two functions to provide a high voltage gain, improve the gain as well as a phase inversion. Okay. All right. So step by step. So this slide is introduced to small signal equivalent circuit, especially with the hybrid pi model. Okay. The hybrid pi model like this one. Okay. A little before. So So again, the real case, the actual BJT amplifier has both the DC bias and AC signal components. We have also learned from the lab 6 and 7. So especially to analyze the small AC signal variation, we, we replace the transistor NPN BJT with a small signal equivalent model. Maybe in this case, again, we have a lot of choice, but we're gonna using to the hybrid, the pi model. Okay, so the input register is sometime R sub in, or the impedance is like G sub in. It depends on the books, but in here is like the input resistance. The input resistance is to, could you see it right there? Connect to here to the ground. Especially, they wanted to see from the inside without part of the voltage sources. So R sub B sub 1, R sub B sub 2, and R sub pi that was R in parallel register. So if you wanted to find R sub in, you have to use that one. Again, I strongly recommend you have to memorize in this circuit. I mean, you can try to make a circuit, equivalent circuit as well. All right, so what is the output resistance? Output resistance, R sub 0 is for the R sub C and R sub 0. Okay, that is like the output register, but maybe inside of the output register AC signal. So R sub 0, R sub C is like the output resistance, and then the voltage gain, the G sub V. Sometimes it was the A sub V, but it depends on the books and instructor. So anyway, so the voltage gain V sub 0 right there, and then V sub 0. Okay. So again, we try to small signal equivalent circuit with a hybrid pi model because to simplify analysis and focus on signal amplification behavior, ignoring DC biasing the effect. So that is what you wanted to do. So the closer to the circuit, I'm going to remove it here. Okay. So right there, you want to see that. Here we go. You're gonna see that the V sub I in here, V sub I is equal, that was the pedal. So R sub V sub one, sub R sub V sub two, uh, V sub pi. It's also V sub I. Okay, that was like the same thing. Especially if we wanted to find V sub I in terms of V sub signal, the voltage divider rule, I sub in plus R sub signal or R sub in time V sub signal. Okay, a different color, get the color for you. Oops, right there. Okay. So the after we found to the R sub signal the input, so we can do something. Yeah, we can do something to V sub I. Okay, so again, the R sub in is 4. So R sub B, 1, R sub B sub 2, and R sub pi in pair. Okay, and then also R sub 0 in here, you know. So R sub C and R sub 0 are in parallel. Okay. So the V sub 0, it is the Ohm's law, IR. So what is I here? This is the current to sources. Do you remember in the saturation mode, the MOSFET, I'm sorry, the BJT working as the current sources. So in here, the I, G sub N, V sub pi, the R is what? So R sub 0, R sub L, and R sub C. Okay. But and then could you see that right there? The current to sources direction like this one. Here, here. Okay. So this is the V sub R sub L in this part is like plus and minus. But the current is minus to the plus. So this is why we have to minus the inversion phasor, the output. Okay. So this is why V sub 0 minus G sub m times V sub pi of R sub C, R sub L, and R sub 0. Okay. All right. So this slide is still keep going, as I said before, but the with new concept for voltage gain derivations. The common emitter amplifier inverts a signal, means like negative sign, as I said before, and provide large voltage amplification depending on the transconductance, G sub n, and then rho the resistance. Okay, right there. So this is what. Oops. Just, sub n, yeah. All right. So the input voltage divisions we learned before in here, right? And the collector output voltage. This is the collector part, okay? So the output voltage right there, keep in mind, this is the plus and minus. Why? Because this is the ground and this is the node here. Usually the current is like this one, but this direction like this one. So the input voltage increase, the transistor definitely conducts more current, causing the collector voltage to drop. Thus, the output becomes inverted, negative sign, giving the common amplifier. So this Y minus sign. This is the view of the Fischker layer. But in here, this is the from the equivalent circuit, we can understand more the easier and also analysis of the circuit analysis. Okay, so the overall voltage gain, this is learned before, G sub V is equal to V sub 0 over V sub signal. Keep in mind, the small signal, equivalent circuit, the overall voltage gain, V sub 0, and then V sub signal. Okay, oops, there. Oops, I'm sorry. One more time, V sub signal, output voltage right there. So the from here, V sub signal is what? R sub in over R sub in plus R sub signal the times V sub pi. Okay, so R sub the V sub signal right there, and then the V sub out, just the plug in here. Um, so the finally, right there. Okay, oops. Yeah, finally, we can get this one. R minus R sub in over R sub in plus R sub signal times the G sub M of R sub C, R sub L, and R sub 0. Okay. So that is for voltage gain, from the circuit, okay, from the small signal equivalent circuit with a hybrid pi model. Again, it depends on the type of the small signal the model. It depends on common sources, you know, it depends on the emitter sources. It depends on the base sources. Definitely, but different voltage gain as well. Okay, and then we have to one more things. Now we have taken R sub 0 into account because it is easy to so remember through this effect, this parameter and discrete parameter, if it's usually very, very small. It's very important. It's maybe R sub 0. So very, very the small. So usually in the real cases, the sample question that was usually is going to 0. Okay. 0.001 is kind of usually we're gonna 0, but it was the more in detail the modeling. So this is why I'm gonna just show you that was connected in panel. All right. All right. So I think we have already done before. I'm going to very quickly go over one more time about the example 3, the common emitter amplifier based on the BJT. The question is the two different one is for the focus on bias design. We're going to learn before this operating point analysis of the common amplifier emitter. And then while exercise 7.42 is performed small signal analysis to determine amplifiers, input resistance, output resistance, and voltage gain. All right, so the first over in here, so that was the given. The I sub E is what? Right here. E, M, that was given, and V sub C plus 6 volt. All right. And then we have to design for DC voltage at the base of 5 voltage. And we're going to find for uh, the DC voltage. Also, we're going to find at the base 5 voltage. Means it's like base of B, 5 voltage. So something like this. The current through the R sub B sub 2 in here, R sub B sub 2, the current here, 50 microamp. Okay, and then V sub CC plus 15 volt, and beta is 100. Okay, and the V sub BE definitely that was like 0.7 volt. Okay, I'm gonna write it here. Oops. Okay, I'm gonna write it here for you. Sorry. Second. Um, I'm gonna just move it here. Sorry. I'm sorry. Confusing. So this is one. And this will be sub 2. Mhm. So I sub B sub 2. Okay, so now one more time, the I sub E. So I sub E is 0.5 milliamp. And V sub C is what? V sub C, 6 volts. Okay. we need to design a circuit for a DC voltage at the base is 5 voltage. Okay. And current through the R sub B sub 2. Here we go. That was for 50 microamp. This is R sub B sub 2. Okay. Now let the V sub CC 15 voltage and beta 100. And then V sub BE is like 0.7 volt. We have to specify value R sub B sub 1 to R sub E and R sub C. Oh, I'm sorry. This is the R sub E as well. No, and then R sub C. All right. So I'm gonna just put different color just to make it clear for you. It's black. No, it's not the black. It's the blue. Blue is better. All right. So that's step one. Um, So the R sub B sub 2, oh, can you see that right there? So R sub B sub 2, the Ohm's law, and 5 voltage minus 0 voltage divided the current, 50 microamp. So that was for the 100 the kilo ohm. Okay, I'm going to skip the calculation. And then the base current is I sub B. We learned before the formula in the long slide in the chapter uh, 5. You can see the chapter 5. Um, so I sub E over here, actually 101 or, sometime 101. It doesn't matter, but 100, it doesn't matter. 0.5 milliamp. So 5 microamp here. Okay. Now, the current is the R sub B sub 1 is R sub B sub 1 in here. R sub B sub 1 is what? Because, let's say, R sub B sub 1 is what? The I sub B. So this is I sub B, the plus, the KCL rule. Okay, so the I sub B plus R sub B sub 2. So, okay. All right. So the I sub B is what? 5 microamp. We calculate before and plus I sub B sub 2 was given. So 55 microamp. Don't be, do not be missing or making mistake, okay? Since the voltage drop across the R sub B sub 1, so is, I'm gonna D here, says the voltage drop across so B sub 1 is B sub CC minus the B sub B. Okay? B is what? B sub R sub B sub 1. This is B sub CC. Okay? B sub CC is so it's like what? The 15 minus 5, the 10 volt. So in here, the R sub B sub 1 is the 10 voltage divided what? 0.055 micro amp. Oh, I'm sorry. This is the 55. Oops, I'm sorry. This is the 55 microamp. Okay. So the after that, by using calculator, the 10, the divided 55, multiply 10 to 6. Well, how can I say? 100 the 82 approximately the kilo ohm. Okay. All right. So, and also still will be going, still will be going. The value of R sub E, we can find the I sub E. Okay. The I sub E. What is the I sub E? The I sub E here, that part, I'm gonna just like this right here. It's right there. Oops. Just on here. Um, so the I sub E is B sub B minus B sub BE and divided the R sub E. Why? Because the B sub B is B sub BE plus voltage drop I sub E times I sub E. Okay. So that is for 5 minus 0.7 that was given. Also, I sub E, we calculate it. It's like 8.6 the kilo. Oh, I'm sorry. So in here, we are looking for the R sub E. So now the R sub E, the I sub E over V sub B minus V sub BE. So 5 minus 0.7 divided 0.5, 8.6 kilo. Right? All right. So the value R sub C, EF, and V sub C is equal to V sub CC minus I sub C times R sub C. Why? Go back to slide. You know, this is V sub C. V sub CC minus, I sub C times the R sub C. Okay. But in this case, I'm gonna do another color for you right there. So the I sub B, it depends, but maybe as I know, it's a really, really small, 5 microamp, 5 microamp. So maybe it's up to you. So usually in the theoretically, oops. So I sub C is approximately is I sub E. Okay. All right. So in here, so 615 minus 0.99 times 0.5 times R sub C. Okay, the other one was given or, we have already calculated before for this one. All right, so maybe it's up to you. Some students may be being confused. The R maybe I sub E, you know, so it depends on the value, but maybe I don't think so. It's a really I sub B is very small, so this is why I sub C almost is same as the I sub E. So the R sub C, so finally is 18 kilo. Okay, the 18 kilo. Oops, this is a really blue one, a little better. All right. So that is for the in here. So maybe again, the other one is I sub B is very big to I sub C. So the due to beta is very large. So that is we can approximate it. Okay. So again, the I sub E is I sub B plus I sub C. I sub E is very small, very, very small. So usually we're gonna calculate it I sub C and I sub E is really similar. Yeah, it's not effective for the. All right, so but this would complete the BIOS design. So the value of G sub n, R sub pi, and R sub 0, we can calculate it, EFG, right there. So this is the formula, G sub n will run before I sub C. This is the what DC value from collector divided V sub T. V sub T, the thermodynamic volt 0.5 millivoltage is kind of the 20 milliamp per volt. Okay. And the R sub pi, this is also G sub M over beta 100 divided 25 kilo ohm. Now, so R sub 0 is V sub A. What is the V sub A? The V sub A is the Pauli effect voltage. Pauli effect voltage. We learned before, right? We learned before. So 100 divided 0.5, that was 200 the kilo ohm. All right. So that is for this the question 7.1, the 41. So now the 7.42 is kind of more the perform the small signal analysis to determine the amplifiers, the input resistance. So that is what I wanted to do. All right. So in here, so as I said before, you have to draw the circuit, okay, from this circuit, and you have to draw with that circuit, okay? You have to do. So it's very important, okay? I assume that you have the draw with that circuit. I'm gonna explain for you right now. Oops. So in here, so we have to find the R sub in H needed to R sub in is what? The R sub B sub 1 and R sub B sub 2 and then R pi. Okay. And this is the 182, 105. I'm gonna skip calculations. So but keep in mind, you have to practice the three value are in parallel. So 4.64 the kilo ohm, and then oops. All right. So R sub 0 is what? Oops. So the R sub 0 is what? The R in parallel. Okay. So R sub in is parallel. So again, usually that was really small one. So sometime we're gonna disregard this one, but I wanted to more in detail modeling here. So I'm gonna deal with in this case. So R sub 0 is R sub C, R sub 0 maybe, or just the R sub C. Okay. Two case depends on. So in this case, we have already the calculated. So maybe 18 and then 200 here because we're gonna also 0, 200 kilo ohm. Okay. Sometimes really small one. All right. So, okay. Then I just so long here. I'm sorry. This is really not played in this case. So that was for 18 plus 200, 18 times 200, it was 16.51 the kilo ohm. Right? All right, the last one, the J, the overall voltage gain we learned before. V sub out over V sub signal. I'm gonna skip the derivation, okay? So that is also we can express R sub in over R sub in plus R sub signal times G sub M, R sub C, R sub L, and R sub 0. So that was my given, okay? That was also given. We have already calculated all of them. The G sub B is, I'm going to skip the calculation, minus 57.3 multiple. Okay? All right. Okay, the last questions. The last question is kind of the design analysis, the common emitter amplifier, the simile one. I'm sorry, this is about too large. get too large, and we can neglect it. So that was the missing the concept. R sub zero is too large, and we can neglect it. Um, so as I said before, in the real BJT, they include the small AC signal, and then the what DC bias signal is like the mix up. So we're gonna try to the value some question. The first question, define the R sub E value to establish DC emitter current about 0.5 milliamp here. And also we're gonna find the R sub C right there. Okay. So collector voltage, the collector voltage plus 0.5 volt, right? And then for R sub L is the 10 kilo ohm. We're gonna draw the small signal equivalent circuit amplifier and determine is the overall voltage gain. All right. So in here, I'm gonna try to do my best. So the R sub E, the what is the R sub E? The R sub E was the given condition I sub E is 0.5 milliamp. So the R sub E, well, we have a lot of condition here. So the first of all, we're gonna assume that this is very small. As I said before, do you remember in the previous one, the I sub E, this is C, B, and E. So the I sub C, the plus I sub B is I sub E, right? But the I sub B is very small, very, very small, right? So well, so just give me a second. Oh, because the beta is very uh the high. So the I sub C from the question is 0.5 milliamp. So the I sub B, the is what? So let's give me a second. I sub C is beta times I sub, okay, the beta times I sub C. Let's say the I sub B is beta IC over the beta is 100, 0.5 milliamp. It's, more 0.005 million. So it's the very small. So it means I'm gonna different color. Here we go. So the I sub C is similar to I sub E, means it is the I sub E. All right. So we are looking for R sub E. The Ohm's law, this is the I sub E. Okay, this is the I sub E. And then um this is the minus 3 voltage. Okay, this is the minus the 3 voltage in here. So for this case, this is the open circuit, you know. So for this case, right there, this is a 0.7 volt. So I'm gonna just like to explain first. Let's say, how can I say, minus 3 voltage, okay, minus the 3 voltage is the equal to I sub E, R sub E, okay, and then 0.7 voltage. Why? Because this is the supply, negative supply voltage. So the R sub E is minus 3 volt minus 0.7 volt and divided the I sub E. The I sub E is what? 0.5 milliamp. So, oops, just give me a second. Um, no, I'm sorry. I'm sorry. I'm gonna just wrong here. I'm sorry. Okay. Oops. So in here, okay, so one more time. Um, minus 3 voltage, okay, is minus 0.7 volt minus I sub E and R sub E. Or 3 voltage, 0.7 volt I sub E times R sub E. So supply voltage is same as the voltage drop, the V sub BE and I sub E, the R sub E. So that is what I want to do. So in here, the R sub E is 0.5 volt. I'm sorry, 0.5 amp minus 0.7 minus 3. Oh, I'm sorry, the milliamp. That was for, there we go, 4.6 kilo ohm. Okay, sorry about that being confused. And then now we're going to looking for R sub C, but the given is V sub C plus 0.5. How can we find the R sub C? The same thing. The 3 voltage, 3 voltage minus the, the 0.5. Why? Because the V sub C is like 0.5. 3 minus V sub C and divided the current 0.5 milliamp is R sub C. That was 5 kilo. Okay. Here, 3 voltage, and then divided the V sub C is what? The given is 0.5 and I sub E that divided, we can find the I sub C. Same thing. All right. So, and C is we have to draw the small signal value right there, V sub signal. So the R sub signal. Okay. So, so the R sub pi and plus minus V sub pi right there, plus minus G sub m V pi, and this is R sub 0. Oops, the R sub C, and also the R sub L. Okay. So as I said before, we're gonna removing the R sub 0 right there because it's too big. So, and also we're gonna just calculate it G sub M I C over V sub T, 0.5 milli amp divided 55 millivolt. This is a thermal voltage, 20 milli a volt. And R sub pi is same thing, beta over G sub M, 100 divided 20, 5 kilo ohm. Now, um, let's say V sub 0 over V sub signal, it is um, R sub pi over R sub pi plus R sub signal, okay, times minus G sub M and R sub C and R sub L. Maybe again, the if we want, you can add in, okay, the R sub 0, but same thing. So in here, and then that was for 5 over 5 plus 0. I'm sorry, 5 over 5 plus 2.5 multiply minus 25 and pedal 10. This is the minus 44.4 and VMB. Okay. So you might be maybe ask me. We have the similar one derivation before in here, especially right there. This is the voltage gain. Um, so you know, uh, the similar one, the V sub pi is what? So R pi, the L pi plus R signal, the over R sub pi times V sub signal. So V sub signal is R pi over R pi plus R sub signal and V sub pi. So if we wanted to in here, and then the V sub zero, definitely V sub pi times of minus G sub m and R sub C R sub L in parallel, or R sub C R sub L R sub zero in parallel. Definitely the cancel out the V sub pi, and finally we can get this the formula right there. All right. Okay. Thank you. Thank you so much. Bye.